Why do religious buildings look like machines? Walk into almost any great cathedral in the world, and a familiar reaction occurs before a single word is spoken. The space overwhelms you. The scale is not merely large, it is precise. Vertical lines pull the eye upward with mathematical intent. Sound behaves differently. Even light appears controlled, filtered, and guided. This response is often described as spiritual awe. But the question worth asking is whether that feeling is incidental or engineered. For centuries, the official explanation has been straightforward. Cathedrals were built to glorify God, demonstrate religious devotion, and symbolize divine authority on earth. Yet when one steps back and examines these structures, not as places of worship, but as physical systems, assemblies of stone, metal, geometry, and space, a different picture begins to emerge. These buildings do not merely represent belief, they behave like instruments. The first anomaly is scale. Many cathedrals were constructed during periods when, according to mainstream history, tools were rudimentary, transport was slow, and engineering knowledge was limited. Yet these buildings routinely surpass modern structures in height, stone mass, and longevity. Blocks weighing multiple tons were lifted to extraordinary heights, with tolerances so tight that even today they challenge replication without advanced machinery. This is not artistic excess, it is engineering confidence. Consider the repeated use of domes and vaulted ceilings. Domes are structurally complex, expensive, and unnecessary for simple congregational gathering. A flat roof would suffice. Even a basic pitched roof would accomplish the same functional goal. Instead, cathedrals consistently employ domes, ribbed vaults, and curved ceilings, forms known in modern physics to influence resonance, airflow, and pressure distribution. These shapes are not accidental, they are solutions. Equally puzzling is the global uniformity of design. Cathedrals across Europe, Russia, parts of Asia, and even the Americas share strikingly similar architectural features, despite being attributed to different cultures, languages, and historical contexts. The same proportions, the same orientations, the same towers, spires, and cross-like layouts. Such consistency suggests adherence to a shared technical framework rather than purely symbolic tradition. Orientation itself raises further questions. Many cathedrals are aligned with cardinal directions, solstices, or specific celestial events. This alignment often required advanced astronomical knowledge and precise surveying, capabilities not commonly associated with the eras credited for their construction. While religion often borrows celestial symbolism, the accuracy seen in these alignments goes beyond metaphor. It resembles calibration. Then there is the matter of materials. Stone is not a convenient choice. It is heavy, difficult to quarry, transport, and shape. Wood or brick would have been far easier and cheaper. Yet cathedral builders consistently selected stone, often specific types with known acoustic and conductive properties. Limestone, granite, and marble dominate these constructions. In modern contexts, these materials are studied for their vibrational characteristics. Historically, they were chosen with remarkable consistency. Metal use further complicates the picture. Copper appears repeatedly, on roofs, in domes and within spires, and in internal fixtures. Copper is not ornamental by necessity, it is conductive. It weathers in a distinctive way, forming a protective patina, suggesting long-term functional intent rather than decorative appeal. If aesthetics were the sole goal, other metals or finishes could have been chosen. Copper persists across centuries and continents. Spire design is another recurring anomaly. These tall, narrow structures often extend far above the main body of the cathedral, sometimes seemingly detached from any practical purpose. They are not needed for bells, nor are they structurally required, yet they are engineered with extreme precision, often capped with metal finials. In modern engineering, similar forms are used for transmission, grounding, or atmospheric interaction. The resemblance is difficult to ignore. Internally, cathedrals display an obsession with symmetry and proportion. Measurements frequently align with harmonic ratios found in music and geometry. Columns are spaced with rhythmic regularity. Aisles mirror one another with near-perfect balance. This is not simply visual harmony, it is systemic order. Modern designers of concert halls and laboratories employ similar proportional logic to control sound and vibration. Lighting provides another clue. Before electric illumination, Cathedral interiors were designed to manage natural light with extraordinary subtlety. Stained glass windows filter, colour, and diffuse sunlight in a controlled manner, preventing glare while maintaining luminosity. Light enters from elevated positions, interacts with stone surfaces, and moves predictably throughout the day. This level of environmental control suggests intentional design beyond symbolic storytelling. One of the most overlooked features is excess capacity. Cathedrals were built to last far longer than the political or religious institutions that supposedly commissioned them. They were constructed with thicknesses, redundancies, and structural margins that exceed necessity. This is not typical of resource-limited societies. Excess capacity implies either abundance or an understanding that the structure would serve a long-term, possibly changing function. Even construction timelines provoke skepticism. Historical records often claim that these structures were built over centuries by generations of craftsmen using simple tools. Yet photographic evidence from the 19th century shows many cathedrals already ancient, intact and operational before modern industrialization. In some cases, restoration documents reveal advanced techniques used long before their supposed invention. At a certain point, the explanation of religious devotion begins to feel insufficient. Devotion can inspire effort, but it does not explain technical convergence across cultures, material choices aligned with physical properties, or design features consistent with modern engineering principles. Cathedrals appear to follow rules that do not change based on denomination or geography. This does not require abandoning the idea of spirituality. It requires expanding it. In earlier civilizations, the boundary between science, spirituality, and technology was not clearly defined. Knowledge was holistic. What we now separate into physics, acoustics, architecture, and theology may once have been understood as different expressions of the same underlying principles. If so, cathedrals may represent a lost synthesis, structures designed to interface with the environment in ways we no longer fully recognize, not merely to inspire belief, but to do something, to channel, amplify, regulate or interact with forces that were once understood intuitively but later forgotten or deliberately abandoned. This section does not claim certainty. It establishes a problem. The problem is not that cathedrals exist, but that their design exceeds their stated purpose. When form consistently surpasses function, the honest response is not dismissal, but inquiry. An inquiry begins with observation. Before discussing sound, vibration, or energy, one must first acknowledge this. Cathedrals do not look like simple houses of worship. They look like systems, and systems are built to operate. The question, then, is not whether these buildings were impressive. The question is why they were built this way at all. When architecture behaves like a tuning device, sound is invisible, but it is never passive. It moves through air, stone, and flesh alike, shaping perception and altering space. Step inside a great cathedral, and this becomes immediately apparent. A single footstep lingers longer than expected. A whisper travels farther than it should. A sustained note blooms, hangs, and dissolves with an almost physical presence. These are not incidental effects. They are the result of deliberate architectural behaviour. In modern design, acoustics are treated as a specialised discipline. Concert halls, recording studios, and laboratories are engineered with precise calculations to control reverberation, standing waves, and harmonic balance. Yet centuries before acoustic science was formally codified, cathedral builders consistently achieved results that rival or exceed contemporary performance spaces. This alone suggests a depth of empirical knowledge that challenges conventional historical narratives. The most striking acoustic feature of cathedrals is reverberation time. Many large cathedrals exhibit reverberation lasting several seconds, sometimes exceeding 10. Such prolonged reverberation would be disastrous in a typical public hall, rendering speech unintelligible. And yet within these spaces, chant and sustained vocalization flourish. Gregorian chants, for example, are structured around long flowing notes rather than rapid syllables. The music fits the building so perfectly that it is difficult to imagine one evolving without the other. This alignment raises a critical question. Did the music adapt to the space, or was the space designed to amplify a specific type of sound? The pipe organ deepens this mystery. Far from being a simple musical instrument, The pipe organ is one of the most complex acoustic machines ever constructed. It uses pressurized air, precisely tuned pipes, and harmonic layering to generate frequencies across an enormous range. Some organ pipes are so large that they produce infrasound, frequencies below the threshold of conscious hearing. These low frequencies are not heard so much as felt, interacting with the body directly. Modern research confirms that infrasound can influence human physiology, affecting mood, perception, and even neurological activity. The presence of such frequencies in cathedral spaces is not speculative, it is measurable. The question is why they were intentionally produced. Cathedrals are uniquely suited to sustain these frequencies. Thick stone walls prevent energy loss. High ceilings allow sound waves to expand and interact. Curved surfaces reflect vibrations rather than absorbing them. Columns act as waveguides, and domes function as acoustic concentrators, redirecting sound downward and inward. These are not accidental byproducts of construction, they are functional characteristics. Consider the geometry. Circular and polygonal forms dominate cathedral design. In physics, such shapes are known to support standing waves, stable patterns of vibration that occur when waves reflect within a confined space. Standing waves are fundamental to resonance phenomena, from musical instruments to radio transmission. In a resonant chamber, even small inputs can produce disproportionately large effects. Chanting plays a crucial role in this context. Unlike spoken language, chant emphasizes sustained tones and controlled breathing. When multiple voices synchronize pitch and rhythm, they create coherent waveforms capable of reinforcing one another. In a resonant space, this coherence can amplify vibration dramatically. The human voice becomes part of the system, not merely an occupant within it. Historical accounts describe chanting practices that lasted for hours, sometimes days. Such sustained acoustic input would have continuously energized the structure. From a modern engineering perspective, this resembles a driven system, one in which external input maintains oscillation. Whether the builders understood this in mathematical terms is unknown, but the behavioral outcome suggests experiential knowledge. Even silence behaves differently in these spaces. The absence of sound is never complete. Ambient resonance persists. Low-level vibrations linger, creating a subtle sensory field. This can induce altered states of consciousness, particularly when combined with dim lighting, repetitive motion, and ritual structure. While often attributed solely to spiritual experience, these effects align closely with known psychoacoustic phenomena. Stone itself plays a role. Certain stones resonate more readily than others. Limestone and granite, commonly used in cathedral construction, transmit vibration efficiently. Over time, repeated excitation can even alter the microstructure of materials, a phenomenon observed in modern ultrasonic engineering. The long-term vibrational environment of a cathedral is not static, it evolves. Pipe organs, bells, and choirs were not isolated elements. They were integrated into a larger acoustic ecosystem. Bells, often housed in towers or spires, produce powerful low-frequency vibrations that propagate through both air and ground. In some cases, bell-ringing schedules followed precise patterns tied to timekeeping, celestial events, or communal rhythms. These vibrations would have travelled far beyond the building itself. Modern studies of resonance reveal that vibrational systems can interact across distances, particularly when frequencies align. This concept, known as sympathetic resonance, allows one vibrating object to induce vibration in another without direct contact. In a dense urban environment filled with stone structures, such interactions would have been magnified. Importantly, none of this requires invoking advanced electronics or lost technology. It requires only an understanding of vibration, resonance, and form, knowledge that predates modern science and was often transmitted through craft tradition rather than written theory. Master builders may not have spoken of frequency, but they knew what worked. The persistence of these designs across centuries suggests that the acoustic behaviour of cathedrals was not incidental. If it were, we would expect greater variation, experimentation, and failure. Instead, we see refinement. Later cathedrals improve upon earlier ones, enhancing resonance, clarity, and sustain. This is characteristic of a technical tradition, not mere symbolism. Why then has this aspect of cathedrals been downplayed in historical interpretation? One reason may be disciplinary separation. Modern scholarship divides architecture, music, physics, and theology into distinct fields. Medieval builders did not. To them, sound, structure, and meaning were inseparable. Another reason may be conceptual discomfort. Acknowledging that cathedrals function as acoustic machines challenges the narrative that pre-industrial societies were technologically naive. It suggests a form of knowledge that does not fit neatly into linear progress models. This does not negate the spiritual dimension. On the contrary, it reframes it. Spiritual experience may have been facilitated through physical means, through carefully engineered environments that use sound and vibration to shape human perception. The sacred may have been experienced not only through belief, but through resonance. By the time one recognizes the full acoustic sophistication of these structures, it becomes difficult to view them as passive spaces. They respond, they amplify, they sustain, they transform inputs into experience. If Section 1 establishes that cathedrals look like systems, Section 2 demonstrates that they behave like them. The remaining question, what these systems were ultimately designed to do, leads naturally to the most controversial possibility of all, that sound and resonance were not ends in themselves, but components of a broader energetic function, from sacred architecture to atmospheric machines. By the time one reaches this point, the central tension is clear. Cathedrals are not merely impressive, they are consistent, engineered, and behaviourally complex. Their architecture suggests system design. Their acoustics demonstrate controlled resonance. The final question, often the most controversial, is whether these characteristics served a purpose beyond ritual and symbolism. To ask whether cathedrals functioned as energy systems is not to claim that medieval societies powered cities or machines in the modern sense. It is to ask something more fundamental, whether these structures were designed to interact with natural forces, atmospheric, terrestrial, or vibrational, in ways that have since fallen outside mainstream historical interpretation. The first element to examine is elevation. Nearly every major cathedral emphasizes verticality. Towers rise far above surrounding structures. Spires extend even higher, often terminating in metallic points or complex finials. From a purely religious perspective, height symbolizes transcendence. From an engineering perspective, height increases exposure to wind, electrical potential, and atmospheric variation. Modern electrical science recognizes that the atmosphere carries a constant electrical charge. The potential difference between the ground and the ionosphere can reach hundreds of thousands of volts. Under certain conditions, this energy can be harvested. Experiments in atmospheric electricity date back centuries, yet the principles themselves are natural and continuous. Cathedral spires resemble devices designed to interact with this gradient. Narrow, elevated, often metal-capped, and grounded through massive stone foundations, they share visual and structural similarities with lightning rods, antennae, and early electrical collectors. Officially, lightning rods were added later, but many cathedrals already possessed the necessary geometry long before formal electrical theory emerged. Grounding is critical here. Cathedrals are anchored into deep foundations, often extending into bedrock. Stone is not an insulator in the absolute sense. It can conduct under certain conditions, especially when moisture and mineral content are present. In modern electrical systems, grounding provides stability, discharge paths, and reference potential. The cathedral's immense mass and foundation depth would have made it an exceptionally stable ground. Copper once again demands attention. It appears in roofs, domes, spires, and internal structural elements. Copper is not structurally necessary for roofing. Other metals could serve the same purpose. Yet copper is repeatedly chosen despite its cost. Its primary distinguishing feature is conductivity and resistance to corrosion. Over time, it develops a patina that preserves functionality rather than diminishing it. Within the building, metal elements often connect vertically. Roof to spire, spire to internal fixtures, fixtures to foundation. While no explicit wiring diagrams survive, the continuity of conductive pathways is visually evident. In modern terms, this resembles a passive electrical network. Domes add another layer. Structurally, domes distribute load efficiently. Energetically, they concentrate and redirect forces. In acoustics, domes focus sound. In electromagnetics, curved conductive surfaces can influence field distribution. The repeated pairing of domes with elevated spires suggests a system designed to collect, concentrate, and distribute something, whether sound, charge, or both. Critics often argue that no evidence exists of energy use, but this assumes that energy must be used in the modern, mechanical sense. Earlier societies may have interacted with energy in subtler ways, stabilizing environments, influencing human physiology, or supporting processes no longer practiced. Absence of documentation does not equal absence of function, particularly in cultures where knowledge transmission was experiential rather than textual. Another overlooked factor is location. Many cathedrals are built on sites of earlier significance, hilltops, crossroads, ancient foundations, or locations associated with pre-Christian worship. Such continuity suggests site selection mattered. In geology, certain locations exhibit higher telluric current activity, natural electrical currents flowing through the Earth's crust. Modern infrastructure sometimes exploits these currents, intentionally or not. If cathedral sites were chosen for their energetic properties, the building itself could act as an interface between earth and sky. This is not mystical language. It is descriptive. A tall conductive structure anchored into an electrically active ground and exposed to atmospheric charge forms a basic circuit. Sound may have played a catalytic role. Resonance can influence physical systems beyond perception. Modern experiments demonstrate that vibration can alter electrical behavior, enhance charge movement, and even induce luminescence under certain conditions. In controlled environments, acoustic stimulation affects plasma formation, particle alignment, and energy transfer efficiency. Chanting, organs, and bells would have continuously energized the structure with vibration. This input may have interacted with atmospheric and terrestrial forces, creating effects not easily visible, but nonetheless real. Even today, resonance-based energy research explores similar principles, often rediscovered rather than invented. Water adds another dimension. Many cathedrals incorporate subterranean water channels, wells, or proximity to rivers. Water is conductive, responsive to vibration, and central to many natural energy systems. In modern hydroelectric and geothermal contexts, water acts as both medium and moderator. Historically, its presence beneath sacred structures may not have been incidental. What complicates interpretation is the collapse of context. Knowledge systems can disappear without trace when cultural priorities shift. The dissolution of guilds, suppression of alternative sciences, and institutional restructuring of education during the early modern period may have severed continuity. Cathedrals remained, but understanding of their deeper functions did not. It is also possible that the energy function was symbolic and practical simultaneously. The same system that produced physical effects could reinforce social cohesion, ritual timing, and psychological impact. Energy does not need to power machines to be useful. It can shape experience, perception, and order. Modern observers often demand binary answers. Either cathedrals were religious or they were technological. This framing is anachronistic. Pre-industrial societies did not divide the world this way. A structure could be sacred precisely because it worked, because it aligned human activity with natural forces. Importantly, this theory does not require a lost super-civilization or advanced electronics. It requires only sustained observation, empirical refinement, and a worldview that treated nature as something to cooperate with rather than dominate. Such knowledge could have existed without leaving the kinds of artifacts modern archaeology expects. Skepticism is appropriate. Extraordinary claims require evidence, but skepticism must apply evenly. The assumption that medieval builders created the most sophisticated acoustic and architectural systems in history purely for symbolic reasons is itself an extraordinary claim. At minimum, the question deserves investigation rather than dismissal. When examined as a whole, the cathedral emerges not as a static monument, but as a dynamic interface. It stands between earth and sky, stone and sound, human and environment. Whether it harvested energy in a literal sense, or facilitated interaction with natural forces in ways now forgotten, its design reflects intention. This trilogy of observations, architecture, resonance, and energy, does not conclude with certainty. It concludes with possibility. Possibility grounded not in fantasy, but in pattern recognition, physical behavior, and unanswered questions. Perhaps cathedrals were never meant to be fully understood by later generations. Perhaps they were products of a worldview in which science and spirituality were inseparable, and where function was embedded within meaning rather than documented separately. What remains undeniable is this: structures built hundreds of years ago continue to outperform modern buildings in durability, acoustic sophistication, and environmental presence. They continue to affect those who enter them, regardless of belief. That alone suggests we are not merely standing inside history. We may be standing inside a system we no longer know how to read. Across architecture, sound, and structure, cathedrals reveal a level of intention that exceeds simple religious symbolism. Their scale, geometry, and material choices suggest systems designed to endure and to function, not merely to impress. Their acoustic behavior confirms this. These spaces do not passively hold sound, they shape it. Chant, organ, and bell transform human presence into vibration, turning architecture into an active participant rather than a silent container. Whether or not cathedrals interacted with natural energy, in a literal sense, they clearly engaged with natural forces, resonance, rhythm, elevation, and environment, in ways modern design rarely attempts. This does not require lost super technology, only a different understanding of how knowledge was once applied. What may have been lost is not the buildings, but the context in which they were understood. In a world where science, spirituality, and environment were inseparable, function did not need explanation. It was embedded in form. Cathedrals still stand because they still work, even if we no longer agree on what that work was. Perhaps the real question is not whether these structures were machines, but whether our definition of technology has become too narrow to recognize them. They do not speak. They simply remain.